Well, it is wonderful to be here in Prague with you, even if only via Zoom. I wished I could be there in real life. I want to make a few initial remarks. First of all, I thank Anston for inviting me, but more importantly, for organizing this workshop of inductive definitions. It is a timely topic. The wide-ranging and yet interconnected topics talks attest to that. There will be even a non-empty intersection of my talk with Ulrich's very informative reflections at the very end of my talk. Secondly, I have been fascinated by inductive definition ever since I started my logical life as a student at the Institut für mathematische Logik und Grundlagenforschung in Münster. It took two different directions when I was a graduate student at Stanford through my dissertation and the work at Patrick Sulpici's Institute for Mathematical Studies in the Social Sciences. The former was connected, as you may know, with generalized inductive definitions and their iteration. The latter was concerned with the formal verification of Gödel's incompleteness theorems for ZF, representing very elementary inductive definition of syntactic notions directly in ZF without arithmetizing them. Thirdly, yesterday morning, or you yesterday afternoon, I had the pleasure of attending Laura's and Mark's talk. I learned quite a bit. As to Laura, her predicativity as invariance allowed me for the very first time to understand why one might want to call the inductive definition of the constructive ordinals O predicative. It has always been my prime example of an impredicative definition. But that's an interesting shift from worrying about sets to the elements of sets. As to Mark, I enjoyed observing the picture Mark drew of an intuitionist theory of inductive definitions. It is beautifully coherent, but also very surprising through the emphasis on language. I appreciated Mark's emphasizing that inductive definitions are fundamental across different foundational frameworks. Indeed, I will argue that different kinds of inductive definitions can be used to characterize foundational frameworks, or the term I prefer, methodological frames. And that very notion is obviously part of the title of my talk. Methodological frame is my translation of the term methodischer Rahmen that was introduced by Paul Bernays in the mid-1930s. He was then struggling to articulate which philosophically distinctive aspects of the finitist standpoint should be preserved when extending it to broader constructive foundational views. Such extensions were obviously needed after Gödel's theorems had refuted the finitist standpoint as an absolute basis for consistency proofs. In his pre-Gödel 1930, a paper that has the title Philosophy of Mathematics and Hilbert's Proof Theory, Bernays viewed mathematics as the science of idealized structures. His introductory discussion highlights changes that transformed mathematics during the second half of the 19th and the first few decades of the 20th century. He pointed to three very early changes. One, the advancement of the concept of set. Two, the emergence of structural axiomatics. And three, the evolution of a theory of mathematical proofs. Against this historical perspective, I will discuss deterministic inductive definitions, or simply ID classes. I will discuss them in a perfectly general way that was formulated by Peter Axtell's contribution to the Handbook of Mathematical Logic, edited by John Burroughs. It appeared in 1977. Pfefferman and I discussed those general formulations in chapter 1 of this volume on iterate inductive definition and subsystems of analysis that Wilfried Buchholz, Sol Pfefferman, Wolfram Bolas, and I edited. The chapter has a title, General Induction, Rule Sets, Operators, and Games. I'm not going to review this, I take it for granted. Axel's way allows the definition of, for example, natural numbers, syntactic logical concepts, formulas and proofs, constructive ordinals, finite and transfinite constructive number classes, as well as segments of the cumulative hierarchy. Given this richness of ID classes, I want to draw a broad, informal image of foundational investigations that may be a little bit old-fashioned, but nevertheless, I like to draw this. Parts of mathematical practice concerned with particular structures and deductive principles are projected into suitable methodological frames. These frames have one common aspect, namely the accessibility of objects and principles. The variety of frames allows differentiating between associated philosophical problems, in particular epistemological and ontological issues. So, to give you an overview of what I want to talk about is, first of all, mathematical structuralism, in admittedly old-fashioned ways, theory of proofs, and then finally ID classes or accessible domains. There is, as all of you know, a standard form of axiomatization in modern mathematics that is not tied to theories of mathematical logic with their formal languages and logical calculi. I'm thinking of the axioms for abstract concepts like that of a group, field, or topological space. The axioms are just characteristic conditions, in German Merkmale, of structural definitions. That perspective, however, was extended by Dedekind to more concrete notions like that of natural numbers via simply infinite systems. The axiomatic method, when conceived of as structural, requires an intelligible and philosophically distinguished methodological frame. For Dedekind, that frame was logic, understood in a very broad 19th century way. The same holds for the early Hilbert and also the early Zermelo. This logical frame allowed novel metamathematical investigations. Such investigations could be carried out because a form of semantics was available. Model is any system that falls under a given structural concept or that satisfies its characteristic conditions. Dedekind had introduced the concept of mapping and thus was able to relate different models in structure-preserving ways. He proved the concept of a simply infinite system to be categorical and argued for the proof-theoretic equivalence of any two models. The methodological frame was also significant for the representation of mathematical practice. In Dedekind's WZ, that's abbreviation for Was sind und was sollen die Zahlen, the representation of elementary number theory was at stake and was achieved through the justification of both the proof principle of induction and the definition principle of recursion. That grounded the systematic development of number theory in the second half of WZ. Other examples of structural concept in the style of Dedekind, well, if you look at Hilbert's foundations of geometry, they're the concept is that of Euclidean space, and in his contemporary axiomatization of analysis, the concept of a complete ordered field. And in Zermelo's first axiomatization, and also in later ones, the concept is that of Mengenbereiche, domain of sets, set domains. In a certain way, Zermelo's 1908 axiom system Z refines Dedekind's logical principles for systems, but jettisons mappings. They are turned into set theoretic objects. Zermelo's system Z developed into ZF during the next 20 years. His investigations über Grenzzahlen und Mengenbereiche can be viewed as a kind of continuation of Dedekind's work on simply infinite systems by establishing quasi-categoricity of that framework. The structuralist way of looking at mathematics, I think, was articulated most sharply by Bourbaki. In their programmatic, The Architecture of Mathematics from 1950, the role of principal structures, structure mère, is brought out. They also clarify what is to be understood in general by a mathematical structure. They say the common character of the different concepts designated by this generic name, mathematical structure, is that they can be applied, these different concepts, to sets of elements whose nature has not been specified. To define a structure, one defines as given one or several relations into which these elements enter. Then one postulates that the given relation or relations satisfy certain conditions, which are explicitly stated and which are the axioms of the structure under consideration. So, characteristic conditions of definitions is, as in Hilbert's axiomatization of geometry, turned into axiom. Bourbaki concludes this passage on structures in general as follows. To set up the axiomatic theory of a given structure amounts to the deduction of the logical consequences of the axioms of the structure, excluding every other hypothesis on the elements under consideration, in particular, every hypothesis as to their own nature. The parallelism to Dedekind, Hilbert, and Zermelo is direct and striking. Indeed, the Bourbaki enterprise is in the structuralist tradition of Dedekind and Hilbert, but refuses to take on their consistency challenge. Dedekind articulated that challenge in WZ and in his famous letter to Käferstein of 1890. He demanded that his foundational frame provide a logical existence proof of a model of the concept simply infinite system. And he asserted that such a proof was needed to guarantee that the newly introduced concept did not contain an internal contradiction. From the very beginning of his axiomatic investigations around 1900, Hilbert formulated this demand in a quasi-syntactic way. He required that no contradiction can be obtained in finitely many logical steps. And I call it quasi-syntactic as no logical steps were explicitly presented. Hilbert formulated in his Zurich talk of 9/11, 1917, some epistemological problems with what he called a special mathematical tint. They all require, he argued, an investigation of the concept of the specifically mathematical proof. That leads me to the second part of my talk, theory of proofs. In lectures Hilbert and Bernays gave in the winter term of 1917-1918 that Hilbert gave, and we have a wonderful presentation of those lectures written up by Bernays, they transformed a part of the system of Principia Mathematica with the axiom of reducibility into a tool for formalizing analysis. Having completed their proof of the least upper bound principle in that very framework, their final comment was, thus, it is clear that the introduction of the axiom of reusability is the appropriate means to turn the ramified calculus into a system out of which the foundations for higher mathematics can be developed. That literally was the final remark. The core methodological questions they had tried to answer was this. Does the subsystem of Principia Mathematica provide a logicist foundation for analysis? If it did, a mathematically rigorous and philosophically satisfying reduction of analysis to logic would have been obtained. In his Zurich talk, Hilbert had reiterated Dedekind's view that mathematics is a part of logic. Fundamental work of Frege and Russell bolstered that view, and Hilbert remarked in this Zurich talk, but since the examination of consistency is a task that cannot be avoided, it appears necessary to axiomatize logic itself and prove that number theory and set theory are only parts of logic. This method, Hilbert continues, was prepared long ago, not least by Frege's profound investigations. It has been most successfully explained by the acute mathematician and logician, Russell. One could regard the completion of this magnificent Russellian enterprise of the axiomatization of logic as the crowning achievement of the work of axiomatization as a whole. So logic was, at that point, considered to be the logic of Principia Mathematica, with ramified type theory, axiom of reducibility, and what have you. The examination of the logicist reduction of analysis leads Hilbert and Bernays in lectures that follow these 1917, 1918 lectures to reject it and to return to the structural axiomatic method. And that method, so in Bernays' description from 1921, he gave a talk at the meeting of the German Mathematical Association in Jena in the fall of 1921, assumes the existence of a system satisfying the structural conditions. Bernays, following Hilbert's considerations that go back to 1904, proposed a different strategy, namely to see whether it is not possible to give a foundation of these transcendent assumptions in such a way that only primitive intuitive knowledge is used. Bernays' programmatic suggestion is brought to life through the idea of projecting structural concepts into a constructive domain and examining the image from a corresponding constructive standpoint. The formalization of the structural notion and the associated systematic development was as the means of projecting. In the pre-Gödel essay I mentioned already, of 1930, one finds this remark. At this point, where one tries to argue for the coherence of structural concepts, the investigation of mathematical proofs by means of the logical calculus is brought to bear in a decisive way. This investigation has shown that the concept formations and the inference patterns used in the theories of analysis and set theory are reducible to a limited number of processes and rules. In that way, we succeed in totally formalizing these theories within the frame of a precisely delimited symbolism. Oh, I'm afraid I left out the figure 1. At least no, I didn't. Oh, very good. Okay, so this methodological situation is diagrammatically depicted in figure 1, which I'm going to show you in a second, making clear the reductive role of the projection. It avoids models and their representation. It rather creates an image in the finitist domain, and that image is to be investigated from the finitist standpoint. Here is the diagram. Structural axiomatics at the very top. Formalization allows you to project the structural axiomatic framework into the finitist domain, and then you investigate the image of this projection by finitist means. So as an exemplification of this methodological schema, consider the structural concept of a complete ordered field as formalized in second-order number theory. In the finitist domain, one has to represent only the elementary formalism, not the infinite objects of its models. Obviously, that idea was pursued, and in 1928, Hilbert gave a talk at the International Congress of Mathematicians in Bologna and reported, among other things, on the work of Ackermann and von Neumann on the consistency program in the finitist spirit of matters. And he asserted in particular that Ackermann and von Neumann had established the consistency of elementary number theory, and that Ackermann was only a small step removed from establishing also the consistency of analysis. Now, that didn't work out quite according to Hilbert's optimism. There was, after all, Gödel's talk or contribution to a roundtable discussion in Königsberg in September of 1930, and a discussion of Gödel's and von Neumann's as to the consistency possibilities for strong formal theories. Von Neumann, I mean, you all know Gödel's work. Von Neumann discussed matters in correspondence with Gödel, and what he discovered, I think, is still wonderfully relevant and interesting. Namely, he argued that the Gödel sentence is actually equivalent to the consistency statement. So that was the end of the finitist program in a strong way. In 1932, both Gödel and Gensten established a reduction of piano arithmetic to Heiting arithmetic. Sorry? Oh, I thought that was a question. Because I'm happy to be interrupted. Okay. So in any event, in 1932, Gödel and Gensten reduced piano arithmetic to Heiting arithmetic. And according to Pernes, in his contribution to the Encyclopedia of Philosophy in 1965, this result showed for the first time that finitist mathematics is a proper part of intuitionist mathematics, and it also opened the possibility of considering wider constructive points of view. So, third part of my talk, ID classes or accessible domains. In his 1938 lecture of Zilsels at Zilsels in Vienna, Gödel noted that Hilbert's finitist program had been attractive to mathematicians, but also to philosophers. He wrote, if the original Hilbert program could have been carried out, that would have been without any doubt of enormous epistemological value. The following requirements would both have been met, would have been satisfied. A, mathematics would have been reduced to a very small part of itself. And B, everything would really have been reduced to a concrete basis on which everyone must be able to agree. Gödel explored in his lecture a variety of extensions of finitist mathematics, from transfinite induction used in Gensen's proof of the consistency of arithmetic to his own system of computable functionals of finite type that led later to the dialectical interpretation. In the same year, 1938, Bernays addressed the very same question Gödel had asked at Silsens. How can one extend the finitist standpoint? He also examined Gensen's consistency proof via transfinite induction and asserted, like Gödel, that this principle went beyond finitist mathematics. Gödel referred to the French 1941 publication of this paper in a letter to Bernays of January 16, 1942. He writes with obvious surprise, I read your article in the Entretiens de Zürich from the year 1938 with great interest. Only what you say on page 152, lines 8 through 11, is not comprehensible to me. Wouldn't that be tantamount to giving up the formalist standpoint? And Bernays' response, I have never taken a formalist standpoint. But in any event, the resulting correspondence is of genuine interest. Bernays articulates in it, in a similar way as he had done in 1938, an open perspective that allows distinguishing between different layers and kinds of evidence. He insists on the methodological significance of syntactic consistency proofs. The task of establishing the inner harmony of analysis from such a standpoint of more elementary evidence as a syntactic necessity by formalizing the inferences of analysis, that task gains in this way its methodological significance. What standpoint of more elementary evidence can be taken? How can one articulate an approach that is based on a more specifically arithmetic character? In subsequent papers, Bernays made some general suggestions. They point in a direction that can be given more weight and significance by exploiting our more extended experience with proof-theoretic investigations. To be suitable for the proof-theoretic aims, Bernays requires that methodological frames must satisfy constructivity requirements, in particular, a crucial condition on mathematical objects. The objects making up the intended model of the theory are not taken from the domain as being already given, but are rather constituted by generative processes. The nature of the objects is as irrelevant for Bernays as it was for Dedekind, but the generative processes give them a unique internal structure. This internal structure is obviously independent of the complete totality of all the generated objects. So let me come back to the Gensen-Gödel result, the reduction of Peano arithmetic to Heyting arithmetic. One can view this result as having been obtained by a projection of the concept simply infinite system through the formalization in pure arithmetic into a subdomain of intuitionist mathematics. A small but significant extension is this reductive result. Namely, one can show that the theory of arithmetic properties, where you have induction only as an axiom formulated, not as a schema, can be reduced to Heyting arithmetic. So ACA naught is conservative with respect to arithmetic statements over piano arithmetic, and that can be reduced by the first result of Heyting arithmetic. So what general features should be required of methodological frames that make them suitable for further extensions of Hilbert's constructivist program turns into a real question, namely, which procedures can be viewed as generative arithmetic rules? And that led in the mid 60s, I suppose, to the concept and introduction of the investigation of generalized inductive definitions. It was started by Kreisel. There is this remarkable Stanford report, and then a summary of investigations concerning iterate inductive definitions and their relations to subsystems of analysis in the volume of Buchholz, Pfefferman, Rudess, and myself. There is one result that I think is still of methodological and philosophical interest, namely the reducibility of Pi11 CA0 to the intuitionistic theory of the finite number classes. It's a combination of result in my dissertation and investigations that had been carried out by Saul Pfefferman. One can view the last two results as having been obtained by a projection of the concept complete ordered field through the indicated subsystems of analysis into a subdomain of intuitionist mathematics. Due to Axel's work I had mentioned at the beginning of my talk, we have an extremely general way of generating mathematical objects. It goes far beyond the arithmetic generation envisioned by Bernays and far beyond generalized inductive definitions. I have called these generated ID classes accessible domains, as their elements are accessible by construction, and as their principles are accessible to our understanding. Let me expand on this remark in my final concluding remarks. In the intellectual background of these foundational investigations lies the contrast between two aspects of mathematical experience, namely the structural abstract and the constructive concrete one. The precise articulation of mathematical and deductive principles falls for me under axiomatische Methode, axiomatic method, axiomatics. Thus, corresponding to the two aspects of mathematical experience, I distinguish between structural and accessible axiomatics. Structural axiomatics articulates, roughly speaking, broad conditions on its models that can have quite different elements. It can serve to make precise analogies between different mathematical situations, and it provides a basis for a deeper understanding of proofs. Accessible axiomatics requires that its models have accessible domains. It yields methodological frames that provide a philosophically distinguished basis for structural axiomatics. The internal structure of elements of accessible domains reflects their generation. If we have a full understanding of the underlying generative processes, the proof principle of structural induction and the definition principle of structural recursion evidently hold. Together, these principles guarantee that different models are canonically isomorphic and proof-theoretically equivalent. And Burgess's slogan of indifference to identification is most appropriate. Here is an ironic twist and a connection to the talk Ulrich gave in the session before this one. In his dissertation, Patrick Walsh characterized accessible domains as initial algebras of particular endofunctors. Thus, he used abstract category-theoretic notions to characterize in a precise way an expansive understanding of the constructive concrete. Thank you very much.